This is the second lecture what we are having, and we are going to learn some more things about our course Digital Electronics and Circuits EL 203. So in the previous lecture we have seen the analog and digital circuits, why we need basically, what are the requirements, what do we encounter in nature in general, and why do we need to shift to digital circuits if analog is anyway sufficient to do things. So first we try to understand what is analog signal or quantity and what is digital signal and quantity. So we have seen that analog means something which is continuous. It may have a range. It may vary between the minimum and maximum range, but it has to be continuous. So we have seen some quantities which are continuous in nature. So current, voltage, power, speed, and temperature, all these things, no, they cannot change abruptly. So that is why these are analog by nature. Now, when we have analog circuits, we have seen that when we are processing these signals, we may have some problems. For example, if we have to process these signals, we need systems which are analog. And analog system primarily consists of all these linear circuits. So it could be resistance or some more things. And when we want to process those, we have lot of issues associated with that. There could be power loss because the electronic devices which are operating in the linear zone may cause lot of losses. So to get rid of that, and then because we have power loss associated with that, so we have cost getting increased, efficiency getting reduced, scalability is questionable. So all these things we are trying to mitigate through our digital design or digital circuits. Now the advantage with digital circuit is that the devices are not operating in the linear zone, but they are operating in two extreme modes. One which is called saturation mode, another which is called cutoff mode. So in both the modes we have very less power loss. This is what we have discussed. And the moment we are able to reduce power loss, all the other features we can very easily include. So our efficiency goes up, cost comes down, and we have scalability and all those things over there. Then further we try to understand how accuracy is better for digital circuits and how it is immune to noise. So we have seen all these things, that when we are trying to convert any analog signal to digital signal, then lot of things are getting removed automatically from the analog circuits, what all problems it may have. And so we understood that this is better in any case. Now, of course, again, this is all what we perceive. It's not any absolute thing that we have analog or we have digital. It's what we can perceive. We cannot have a very perfectly continuous signal, let's say x equal to sine omega t. Still, there are infinite points theoretically. That's what we have discussed. But we cannot have all those points, let's say when we are writing it down in a table or using it somewhere, we cannot have all those points. Even temperature, speed, that cannot change very, very slowly. Let's say of the order of 10 raised to power minus 15 or minus 12. This is not possible. So again, it's all perception, how we are seeking the systems or how we are looking at the signal or the systems. Now, once we have understood that yes, digital has some advantages, and we should basically, and we are actually shifting to more and more digital circuits and digital systems. So then we need to understand few more things associated with that, the basic things which are related to any digital design. So if we talk about the digital circuits and systems, we first need to understand how it operates, because we know there are only two states. We call it yes or no, or 1 or 0. This we have understood, right? Yes or no?
Yes, sir.
Okay, keep your mic on so I can hear what you are saying. So then we have only two states to or define any signal or any system, which means automatically we are somehow bound to this number 2. Generally, whatever number system we deal with, so that is having a base of 10. So what is meaning of base 10? Anyone?
Sir, the radix is 10.
Okay, what is radix?
Sir, it denotes the weights, sir.
Weights, okay. So which weights are you talking about?
Sir, the
So number of
every bit is associated with
number
a
of
weight.
digits we use is 10.
The
Correct.
unit
Number of different numbers available within a particular system.
Yes. So when we are talking about number system which we normally encounter, so which has base value 10 or radix equal to 10, we are automatically referring to a system which is position based, or we can also call it position number system, which means any integer you are writing x, it carries a value that depends on its position where it is, isn't it? Let's say you write a number xyz or zyx. Now this z and x are interchanging their positions, so the value associated with these are also changing. Is that what you mean by weights also?
Yes, sir.
Correct. Now, naturally, what we are encountering is this radix r equal to 10. Now, when we say r equal to 10, what are the possibilities for our x, y, z, whatever we are writing? So what are the possibilities for x, let us say?
0 to 9.
Yes. Why don't we write 10?
So 10 will be a 2-digit number.
One by one.
It's not a single digit, sir. It represents two different digits.
Exactly. So in any number system, whenever we say, we are representing one digit or bit or a single place, we can say in general, because digit is something which is related to 10, bit is something which is related to 2. We may have something else as well, some other r also. So yes, of course, the possibilities for x are between 0 and 9. Now, what you said is correct. Let us say there is a number. If I give you, for example, this 1734 and having base value 10. So how would you perceive? No? How would you understand what this is saying or what value it contains? So obviously you go by weightage. How do you go by weightage? Each and every place is having some weightage in terms of this radix value. So this first position, we have weightage of 10 raised to power 0. The next one has 10 raised to power 1. Next one has 10 raised to power 2 and then 10 raised to power 3. And that is how we read this also. So we will write something like this if we are trying to understand the value of this number system, isn't it?
Yes, sir.
Yes, sir.
So we may also have something which is having a decimal. So less than 10, let us say this. Now how do you understand this?
So 10 raised to power -1 and then 10 raised to power -2.
Yes, exactly. So you are seeing this decimal place, again we are calling it decimal because it is associated with 10. So we may call it some binary point when it is related to 2, or we may call it some other name if it is associated with some other r. So before, I mean not before, after, but let's say the right hand side and left hand side, if we are having, so it's how you are seeing the board, let us say. So on one side we have all the positive integers as the weightage of this numbers, and here all we have negative integers. So Simply, if we have to understand this, it's very, very easy to write. Isn't it? Any problem in this?
No, sir.
And this is how we understand that what this number is trying to indicate, what weightage it contains, isn't it? Now, whatever we understand, that becomes the basis of creating any other number system also. Now, in general, if let us say we have to give a number system at base 10 or any number we have to write at base 10, some digits we can write that will be in this form. Let's say and so on. It can go on this side and this side, isn't it? So here what we are trying to do, we are trying to break the number in terms of what is the digit that is at that position and what is its weightage. In these two parts we have divided this, isn't it? And what are the possibilities for all these, whatever D3, D2 we have written? So let's say Di, that it has to be between 0 and R minus 1, or if we are writing 10, then 10 minus 1. Understanding my point? Yes or no?
Yes.
Yes,
Yes,
sir.
sir.
Yes, sir.
In general, what we can say that any number, if we are writing in any radix system, can be written as some summation of this I equal to minus q to, let's say, p minus 1 di ri. So p is the highest on the left hand side what you have, and q is the lowest what you have on the right hand most digit number. Understanding my point? Now when we are saying
Sir.
this, yes.
Can you again explain that DI? There was a network issue.
Yes, sure. So again, if you try to write this, what we are basically, if you expand this, so what we have basically is that d p minus 1 r raised to the power p minus 1 plus d p minus 2 r raised to the power p minus 2, and so on. It will go on up to d1 r1 plus d0 r0, or again, further it will proceed at d minus 1, r minus 1, d minus 2, r minus 2, up to d minus q, r minus q. So these are the positions. This is what is written in a compact manner. Now here we have generalized for any radix r. This is how we can represent any number in which format. This is what we perceive. So obviously, this is our natural radix system we are transforming to, which is 10. So if you write or expand any number system in this form, basically you are perceiving it at the base of 10. Understanding my point? I will explain a little bit more on this. So this point is clear, right? How we are expanding this, it should be obvious.
Yes.
Now here, one thing first what I want you to understand is the significance of these bits, how important these are. So obviously, as we are going towards the right hand side, these becomes lesser and lesser significant. So this is the least significant bit, what is on the extreme right side, and this is the most significant bit, what is on the extreme left. And so your accuracy also changes with any mistake on these bits. Understanding my point? So this is the thing you first understand over here. Now, what I mean by saying that this is our representation of any radix system at base 10. So for example, if we go for r equal to 2, 2. So what are the possibilities for any bit, let us say di?
0, 1.
0 and 1.
These are only two possibilities. Now, simple example, if I have to write any number, let's say b, if you are writing 1011 at base 2. So always put a bracket and put the base value so that you understand which number system you are referring to. Now someone asks that what is this representing? What is the value of this? So how would you say?
We'll convert as-
Yeah,
we'll convert as-
yeah, how? Tell.
Sir, multiplying the summation of di r to the power I.
Correct.
R
So now how
R
many
is equal
places
to-
are there? There is no decimal point or anything on the right and left side. So it's all, we are talking about zero or positive integers on the power. So power of what? Power of 2. So r is equal to 2 over here. Now how would you write this? Can you expand?
Yes, sir. Sir,
1 into 2 cube
Hmm.
plus 0 into 2 to the power 2
plus 0 into 2 square
Yes.
1
plus 1 into 2
1 into 2.
plus 1 into 2 power 0.
Isn't it? Now once you write this, now which number system you are referring to? Once you expand this. The moment you expand, you have automatically come down to your natural base, your natural radix system. Because this is
Base
where
10.
you perceive what is 2, what is 1. This r equal to 2 cannot understand what is an integer 2 or more than 2. So anything, this d greater than or equal to 2 cannot be perceived by this. Understanding my point? So the moment you say what is the value and you write in this form, this is, you are referring to the base value 10. Now you can tell what is the value of this number. Anybody?
11.
11.
11.
Okay. This is at base.
11 to the base 10.
Huh? So this is how you represent 11 in r equal to 2 base, like this 1011. Clear? Or vice versa. If you are given the number 1011, you represent it as 11 at base 10. Correct? So similarly, for exercise, you may have more numbers to, let's say, if I say some bigger number 100010, again at base 2. So quickly you can convert and tell. So someone, quickly can you tell what is the number over here?
Sir, I have a doubt.
66.
34.
34
34.
Yes.
34.
What is the doubt?
Sir, how did it automatically get converted into base 10? Like,
Yes.
why only
So,
base 10?
yes, which is what I was trying to make you understand, that our natural understanding holds on this base r equal to 10, isn't it? On this radix system. So whatever numbers, when we are talking about that, it can be written in this form, which means this is originating from this. Okay, let me little bit more elaborate this. Let's say I tell you another number system r equal to 5. Understanding my point? Now what are the possibilities for di?
0 to
0
4.
to 4.
0 to 5. 0 to 4.
These are the possibilities. Now tell me any number with this radix system. Any 3-digit
0,
number.
1, 2, 3, 4.
So any 3-digit
0.
number, this radix system.
1, 2, 3.
Okay, let's say 1, 2, 3 at base.
1.
So when I ask you what is this 1, 2, 3 given at base 5, what would you do?
Convert into base 10.
Convert to natural radix.
No, why are you converting to base 10?
we easily interpret that value.
Yes, it is not about easily interpreting, but it's about only interpretation what we have is at base 10. We don't know what 1 is or what 4 is or what 3 is unless we tell that which number system we are referring to. The moment we say which number system, that means obviously that number system is derived from somewhere. Understanding my point or not?
Yes, sir.
We do not have any other means to understand what this number system is. So the moment you write this in this form, no, di r raised to the power I, so this itself is referring to your what you can understand. Getting my point?
Yes, sir.
Even r, when you are representing r and r raised to the power I, all that is happening naturally at 10. You don't know what is r raised to the power I in some other number system, let's say r equal to 5. Getting my point?
Yes, sir, I got it.
So this is what I am trying to say, that the moment we talk about, okay, this number contains this value. So this representation itself for any radix system itself is conversion to radix r equal to 10. This is the straightforward conversion for r equal to 10. Otherwise, how would you say what this number 123 or 1011 or any other thing is? Clear?
Yes, sir.
Okay. Now another property we can say, if let us say we have multiple bits, let's say we are talking about r equal to 10 and we have multiple bits, let's say 2 bits, and we are continuously incrementing this number. So what will happen from 0 0 we will go to 0 1, so incrementing by 1, we are adding only plus 1. So next it will go and reach up to 0 9. So what will happen after that if you again increment 1?
1 0.
Isn't it?
1 0.
So this rollover, what is happening on these bits, do you see any correlation with the previous one? Let's say when this lower significant bit has rolled over by 10 times or is incremented like no from 0 to 9 and then incremented once more, then only this bit is changing. Are you understanding that?
Yes, sir.
Yes, sir.
So this pattern is another property which we have in all the number systems. So unless the previous bit changes from 0 to r minus 1 completely, the next bit, the next significant bit cannot change. Fine. So now the next number, if you want to increment, it would be 1 1. And so on, it will go on up to what? Let's say 1 9. Now what after that?
Right.
What after this?
Then the second significant bit will change.
It will change to 2 0. And so on if you reach up to 9 9 then.
Yes, sir.
Then first will
Third
change
bit.
and second also change.
So what it will become?
100.
100.
One,
Where is 100? There are only 2 bits over here, right? 2 digits. It will roll back to its previous, the original value 0 0.
0 0.
Understanding my point? So this is the property of this number system. How many digits we have or how many bits we have, that indicates what is the maximum, maximum number we can represent with this available number of bits or digits. If let us say there are n for base 10, then how many numbers we can represent? What is the maximum number what we can represent? Can you tell?
So 10 to the power n.
10 to power n.
10 to the power n is correct. That is the total numbers what we can represent. But maximum number or maximum integer when I'm talking about, it is minus 1 because we have 0 also being represented in the same system. So if you have n equal to 2, then you have limitation that you can go only up to 99 for r equal to 10. If you have n equal to 3, you can go up to 999. Understanding my point? So if you are trying to represent any number or any quantity, you must understand whether you can represent this with available bits or not, with available digits or not. If not, then what you need to do, you need to increase your number of digits to accommodate that extra information what you are having. Now, for this n equal to 2, whatever comes after 99, that all information is lost. And for n equal to 3, whatever number or whatever information comes after this triple line, that is all lost. We can only perceive up to this. We can only receive and transmit only up to this. So this is another limitation. Understanding my point? Yes or no?
Yes, sir.
So generally any number system, we will have this incrementing sequence which will reach the maximum and then it will come back to its original value 0, 0, 0. So we will talk about signed and unsigned numbers later on. But as of now, you take these as all positive integers. Then this is how the number system goes. It's like a ramp which is going and then coming down, again a ramp going up and coming down. Fine. So from here to here, the jump requires only one increment, plus 1. Clear? Now this is what is true for any other number system also. Let's say r equal to 2. If I have 3 bits, then I can go only up to maximum what? What is the maximum number what I can represent with this?
1, 1, 1.
1, 1,
111. And what is this number in our natural number system?
7.
How do you get 6? So this is the maximum what you can represent using these 3 bits. This is what we were talking about, the accuracy, and we can expand our number of bits if we want to have more information. So let's say we have to represent only integers up to 5. So how many bits we would need to accurately represent this?
2 bits.
Sure.
5 raised to the power n.
3.
3 bits.
3 bits. Of course, we will have some bits unused. So we may have unused bits, but we cannot afford to lose any information. If you have to represent only up to say integer 3, then only 2 are sufficient. Here you don't have any unused, maybe 1 may be unused. Or if you are saying about 0 to 3, yes, all are used. So no unused bit. But the moment you go beyond 3, you have to use 3 bits. Whether you are utilizing all the bits or not, that is a different issue. Is that clear?
Yes, sir.
So always we have range.
I am confusing. Sir,
Yes.
I am confusing with the bits. What do you mean by bit? Digit
What do I
or-
mean by? Say a little louder.
What do you mean by the bits? The bit term. Bit is a number or?
Yes. So do you understand digit?
Yes, sir.
What is digit? What is digit? Don't worry, whatever you know, you say, it doesn't matter.
Representation of some value, a symbol of a value.
Yeah, so basically digit is what? Digit is just one place. So in any number system, when we are talking about, always we have some few places which we are trying to fill with numbers, isn't it? Yes or no?
Yes.
So digit is referring to basically this each position what we have. Let's say anything A, B, C, D you are filling over here, then this is referring to each and every position. When we say there are 4 digits, so which means what? Yes, we are filling 4 positions, isn't it?
Yes. Yes, sir.
Digit generally refers to r equal to 10 automatically. This digit or decimal, so wherever these things are coming, these are all derived from something related to 10. So same thing when you want to correlate for r equal to 2, it becomes bit. Understanding my point?
R equal to 2?
Yes.
Okay, sir.
Shivanshu, is that all right?
Yes, sir.
So basically we are referring to positions, what we are trying to fill. So that's what we say, how many bits we have. 1, 2, 3, 4, 5. So we have 5 bits. We have 5 positions to fill. So we have to discriminate somehow between r equal to 10 and r equal to 2, because this is what the computers are perceiving very naturally, and this is what we are perceiving very naturally. So somewhere we have to discriminate in our language. That is why we go for a different term for digit, which is called bit. Nothing else. It's not something very different or something very special. Getting my point?
Yes, sir.
So this is what it is. So that is what I say, that how many number of bits or how many number of digits are there, that indicates then what is the maximum integer or maximum number. So basically integer only we say as of now, because it's all giving weightage and taking the positive value. We are not talking about where is the dot or decimal place and all that. So what is the maximum integer what you can afford to accommodate in these available places? Is that clear?
Yes, sir.
So if let us say there are 5 bits available, then what is the maximum integer what you can accommodate?
31.
Yes, 2 raised to the power 5 minus 1. And how many numbers you can have? So maximum integer and maximum number of integers, these two are different things. No, this at least little bit focus you need to have on what I'm saying. So total number of integers what you can have is 32. But the maximum integer could be 31 because you are including 0. Fine?
Yes, sir.
Now let us go to something interesting. Okay, let's say I tell you that you have to convert one number to binary. Let's say 179 and given at base 10, and you want to convert it to r equal to 2. So how do you do?
So first divide by 2 and then store the remainder. Then Successively divide by 2.
Exactly. So again, I am referring back to the this representation what we have given. Basically these all di what we are writing, these are what? These are the reminders of all the divisions what we are having with this base value 2. Understanding my point?
Yes, sir.
Yes, sir.
So yeah, quickly can you keep telling how would you convert this 179 to R2 or base 2?
So divide by 2 and keep storing the remainder until we get to
Okay,
0 or
then
1 in
what
the
is
end.
the remainder?
89 into 2 plus 1.
Is it?
Yes,
Then
sir.
next. Next.
It
Or you will start sleeping.
44
Next,
into
what
2
we do?
plus 1.
Divide this, and what comes out?
44 and 1.
So let's say, I mean, to discriminate, let us keep writing what this is representing. So this is 0th position, then this is first, then keep on going.
22 and 0.
0.
Okay.
11 and 0.
0.
Okay.
Then 5 and 1.
Okay.
Then 2 and 1.
Okay.
1 and
Then 1 and
Then
0.
1 and 0.
1 and 0.
That's all. Something else.
That would be all.
That
0
would-
and
1.
Unless you get 0 at this place, you have to keep doing that process. So how many places we have, how many bits we have over here?
7 bits.
8.
8 bits.
8 bits.
8 bits are there. Now, can you write all out what this number has become? 179.
1 1 0 0 1 1.
So always we start writing from what? Least significant bit, right?
1 0 1 1 0 0 1 1.
1 0 1 1 0 0 1 1.
Is that correct?
Yes.
Yes, sir.
Something is missing.
1
One
0
number
1
is
1.
double one, double zero, then double one, and then 0 1. Is that correct now?
Yes, sir.
See, now
Yes, sir.
you understand this, why I am taking this exercise. Simple small number 179 is what? It's a small number compared to know what all big numbers we are dealing with in our day-to-day routine. And how many bits? 8 bits you are writing for this. So imagine if you have to do this process for all the big numbers throughout all these computations and all, a normal person will go mad, isn't it? Having 8 bits, then let us say you have something like 250, you may have more number of bits. So how much space do we need to write these simple things? And how do we process ourselves? Okay, for computers it is fine. They have to process in that manner and we have provisions for that. But what for us? What about us? We cannot keep writing no number of pages after pages for this thing, isn't it? For example, let's say, this is a very, very practical example. Anyone, what is your roll number?
20 115 105.
Is that? Is it correct?
There is lag, sir. I can speak 20 115 105.
Correct, right?
Yes, sir.
So is my screen visible to all of you properly or is it lagging?
It's
Sir,
correct.
it is visible.
Okay.
Well, sir.
Now you imagine if you have to convert this number to this R equal to 2. And how many students are there? 175. So can you imagine how much space would be needed to only write it in this form? Any response?
Yes, sir. It will be a tedious task.
Isn't it? Then why we are doing all this? We should have a better way to represent, at least for our understanding. Computer will process it bit by bit. That is a different thing. It can process very fast. We have the algorithms, we have the circuits for that. But for our convenience, for our understanding, we should have a better method to represent it. Isn't it?
Yes, sir.
So what we do? What are the options? Can you suggest?
So use higher powers of 2.
Exactly. So what we can do, we can club. Let us say 179 is written as 10110011. Now what we can do, we can club, let's say 2 together. Now instead of 8 places, we will need only 4. Let's say we write the exact value, what this is containing, these 2 bits, whatever are coming. So this will be like 2, then this will be 3, 0, 3. At base value sum 4, because this is 2 raised to the power 2. Getting my point? Yes or no?
Yes, sir.
Now this is one option. Then why stop at 4? Why not go for 3, combination of 3 bits? So that is what we call as radix 8 or the octal number system. So we have r equal to 8 because 3 bits we are representing together in this number system. So what possibilities we have for our digits or for our bits in this number system?
0 to 7.
0 to 7.
Correct. These are the possibilities, and obviously this is the number which we can represent in our 3 bits for r equal to 2. Maximum number what we can afford to have is actually 111 for base 2, which is 7. So if this number 179 we have to represent in r equal to 8, 10110011, what we will do, sorry, this is 2 still. We will club 3 bits together. So we may have one or 2 bit shortage at the end, so we can add some extra bits, 0 at the end, and we can represent these 3 blocks together. Now what this number would become?
263 base 8.